This is first order linear ordinary differential equations, part 4. We will look at a physical application, a flowing fluid that has salt water in it, and that salt water is mixed with other water of a different concentration. Let's look at a saltwater mixing problem. At time t equals 0 minutes, a tank contains 1 pound of salt dissolved in 20 gallons of water. Salt water is pouring into the tank at 3 gallons per minute. This salt water inflow has a half pound of salt per gallon. The water in the tank is continually thoroughly mixed and leaves the tank at 2 gallons per minute. First, let's find x of t, the amount of salt in the tank after t minutes. And we also, second, want to find the concentration of salt, c of t, after t minutes, measured in pounds per gallon. So here's the situation. We have a tank with a saltwater mixture in it. Water is flowing in at a rate of 3 gallons per minute, and this salt water has a half pound of salt per gallon. We also have water flowing out of the tank at 2 gallons per minute, and right off the bat we don't know the salt concentration of this mixture flowing out of the tank. However, if we look at this for a minute, the concentration of salt coming out of the tank at a particular instant of time has to be the same as the concentration of salt in the tank at that time. The idea here is that salt molecules are neither created nor destroyed. It can flow from one place to another. And so we could ask, how fast is salt entering the tank in pounds per minute? How fast is salt leaving the tank in pounds per minute? And then, how fast is the amount of salt within the tank changing in pounds per minute? If you also look at this, you'll notice that water is flowing in at 3 gallons per minute, and it's flowing out at 2 gallons per minute. So for each minute that passes, there's 1 more gallon of water in the tank. The water level will rise. We will assume that it can rise indefinitely. We will not have a bound on that. So let's set up a function. Let's let x of t be the amount of salt measured in pounds within the tank at time t. Let's let c of t be the concentration of salt within the tank after t minutes of flowing, and let v of t be the volume of fluid in the tank after t minutes. So v of t will be measured in gallons. Since we have 3 gallons per minute entering the tank and 2 gallons per minute leaving the tank, the volume of fluid in the tank increases at 1 gallon per minute. So we can say that V of t is equal to 20 plus t. The original 20 gallons that were in the tank, and after t minutes there are t more gallons of fluid in the tank. So let's think about the concentration of salt in the mixture inside the tank after t minutes of flowing. The concentration of salt is going to be the amount of salt in the tank at time t divided by the amount of fluid measured in gallons in the tank at time t. We just saw that V of t is 20 plus t. So C of t is equal to x of t divided by 20 plus t. So the rate of change of the amount of salt within the tank, dx dt, equals the rate salt enters the tank minus the rate that salt leaves the tank, measured in pounds of salt per minute. So dx dt then is equal to the rate the fluid enters the tank, measured in gallons per minute, times the concentration of salt in that entering fluid, measured in pounds per gallon. And then subtract off the rate the mixed fluid leaves the tank, measured in gallons per minute, times the concentration of salt in the mixture. Now let's look at each of these 4 factors in those 2 terms. The rate that fluid enters the tank in gallons per minute, problem told us that was 3 gallons per minute. So here's the 3. The concentration of salt entering the tank, well, we were told this fluid had a ½ pound of salt per gallon. So this factor is 1/2. Then we subtract off the product of these two factors. The rate the mixed fluid leaves the tank, measured in gallons per minute, we were told that that was 2, and here it is. Now, what about the concentration of salt in the mixture? At any instant of time, the concentration of salt in the mixture leaving the tank is the same as the concentration of salt in the mixture that's in the tank, and that was equal to the amount of salt in the tank, x, divided by the amount of fluid in the tank, 20 plus t. So we get dx dt equals 3 times 1/2 minus 2 times x over 20 plus t. So doing just a little bit of rearrangement, we have the differential equation dx dt equals 3/2 minus 2x over 20 plus t. That's the differential equation for x of t, the amount of salt in the tank at time t. We were told also that at time 0, there was 1 pound of salt in the mixture inside the tank. So x of 0 is equal to 1. We have a differential equation and an initial condition. Together, those give us an initial value problem. So first, let's solve the differential equation. So we had dx dt equals 3/2 minus 2 over 20 plus t times x. Let's rearrange those terms to get dx dt plus 2 over 20 plus t times x equals 3/2. If we look at this, it is in the form dx dt plus p of tx equals q of t. This is a first-order linear differential equation. So the integrating factor in this case is going to be a function of t. The p of t function is 2 over 20 plus t. So mu of t is e to the integral of 2 over 20 plus t dt. And this integral is fairly easily evaluated to get 2 natural log of 20 plus t. So the integrating factor is e to this exponent. But then we can rewrite this using properties of powers as e to the log of 20 plus t quantity squared. But e to the log of 20 plus t is just 20 plus t. And then we have the square here. So the left-hand side of this differential equation can be written as the derivative with respect to t of the integrating factor times the left-hand side of that differential equation equals the integrating factor times the right-hand side of that differential equation. So here we have the equation from the previous slide. The left-hand side, we realize, can be written as the derivative with respect to x of the integrating factor times x. And the right-hand side just remains unchanged. Now, let's anti-differentiate both sides of this equation. When we anti-differentiate the left-hand side, we get x times 20 plus t quantity squared. On the right-hand side, we'll just have the integral of 3/2 20 plus t squared dt. Now, if you look at this right-hand side for a minute, if you let u equal 20 plus t, then du is going to equal dt. So what we basically have here is the integral of 3/2 u squared du. That is an easy integral to evaluate, and then we can back substitute the fact that u was 20 plus t. And so this right-hand side becomes 3/2 times 1/3 20 plus t quantity cubed plus an arbitrary constant of integration. The left-hand side remains as it was. So here's the equation that we had on the previous slide. If we solve this for x by dividing both sides by 20 plus t quantity squared, we have x equals 1 over 20 plus t quantity squared times all of this stuff. When you multiply this out and simplify, you get 1/2 times 20 plus t plus an arbitrary constant over 20 plus t quantity squared. So this x of t equal 1/2 20 plus t plus c over 20 plus t squared is the general solution to the differential equation. We want to solve the initial value problem, so we're looking for the function x of t that also satisfies x of 0 equals 1. So if we plug in 0 for the t here, and thus zeros for the t's over here, this expression should equal 1. And so that's what we have here. 1/2 20 plus 0 plus c over 20 plus 0 squared equals 1. Go through the arithmetic and you find that c is minus 3600. So the amount of salt in the tank at time t, that is after t minutes of flowing, is x of t is 1/2 the quantity 20 plus t minus 3600 over 20 plus t squared pounds. We also asked, what is the concentration of salt within the tank after t minutes? Well, remember that the concentration is just the amount of salt in the tank divided by the volume of the fluid in the tank, both at time t. We just found what x of t was, and so we just take that previous formula for x of t and divide it by 20 plus t. And so here we have the 1 over 20 plus t times this stuff, which is x of t. And when you simplify it, you get 1/2 minus 3600 over 20 plus t quantity cubed. So that's the concentration of salt in pounds per gallon in the tank after t minutes. So we have finished solving our initial value problem. So let's talk about long-term behavior in this problem. What happens to the salt concentration as t goes to infinity? What is the limit as t goes to infinity of c of t? Well, c of t, remember, was 1/2 minus 3600 over 20 plus t quantity cubed. And as t goes to infinity, this denominator goes to infinity. So 3600 divided by denominators that get huge goes to 0. This fraction goes to 0 as t goes to infinity, and so the limit is just going to be 1/2 minus 0, which is 1/2. In the long run, the salt concentration in the tank approaches the concentration of salt in the fluid entering the tank. So let's construct a computer simulation of our problem. Our goal is to numerically simulate what happens in this dynamic mixture problem, salt water entering and leaving a tank. We will see how the salt concentration changes second by second. The simulation will not use differential equations nor calculus. We'll write a computer program written in MatLab to perform the simulation, and afterwards we will compare this numerical solution with the exact solution that we achieved so far. In our program, we'll have the following variables. We'll have an array x, and let x sub n be the concentration of salt measured in pounds in the tank after n seconds. Let's let v of n be the volume of fluid measured in gallons in the tank after n seconds. And let c of n be the concentration of salt measured in pounds per gallon in the tank after n seconds. Notice that everything here is going to be measured in seconds, not minutes. In the original problem, we stated the problem in terms of minutes. So our initial conditions are the initial amount of salt in the tank is 1. The initial volume of fluid in the tank is 20 gallons. And so the initial concentration of salt in the tank is 1/20th of a pound of salt per gallon. Let's ask a question of concentration of salt water, that is. Here's the question. I have a glass filled with salt water. It is thoroughly mixed. The concentration of salt in the glass is 1/20th pound salt per gallon. I pour out half a glass of the salt water. What is the salt concentration in the remaining salt water in the glass? To answer this question, we could look at it the following way. After you pour half of the salt water out of the glass, then 1/2 of the salt, measured in pounds, remains in the glass. 1/2 of the volume of the fluid, measured in gallons, is still in the glass. So when you look at the concentration of salt pounds per gallon, that concentration does not change. So let's ask ourselves, how do things change in that tank of salt water second by second? We'll think of starting at time n in seconds and going to time n plus 1 second later. We're going to do three things during that 1 second. We're going to let 3/60ths of a gallon of salt water enter the tank. We'll mix what's in the tank thoroughly, and then we'll let 2/3 of a gallon of salt water leave the tank. So let's start with the first step. We let 3/60ths of a gallon of salt water enter the tank. Then, since in that entering water there's a half a pound of salt per gallon, we have 3/60ths times a half pounds of salt entering the tank. The volume at time n plus 1 is going to be the volume of fluid in the tank at time n plus that 3/60ths of a gallon. The amount of salt in the tank at time n plus 1 is the amount of salt in the tank plus the additional salt, which is 3/60ths times 1/2 pounds, which enters the tank. We mix the stuff in the tank thoroughly, and so the concentration of salt in the tank at time n plus 1 is just going to be the amount of salt measured in pounds at time n plus 1 divided by the volume of the fluid in the tank at times n plus 1. The third step is to let 2/60ths of a gallon of salt water leave the tank. Then we have 2/60ths times C of n plus 1, the concentration at time n plus 1, pounds of salt leaving the tank. So that tells us then that the new amount of salt in the tank is going to be reduced by this concentration times 2/60th. The volume of fluid in the tank at time n plus 1 is reduced by 2/60ths, and the concentration of salt in the tank, pounds per gallon, is the amount of salt in the tank at time n plus 1 divided by the volume of fluid in the tank at time n plus 1, and that is equal to the number that we previously computed over here. We have to worry about one technicality in writing our program. MatLab does not allow an array to have an index of 0. The arrays must start with index 1. So in our program, x sub 1 will be the initial amount of salt in the tank at time 0, v sub 1 the volume, c sub 1 the concentration at time 0 seconds. So the index of the array is 1 more than the actual time. Let's just consider here is our MATLAB program. It should run exactly as shows in MATLAB. A graph using a clone versus C of MATLAB, C an open source the numerical approximation called Octave of the saltwater concentration. And this program, our MATLAB program, exactly as we saw this figure earlier, is T lecture versus the exact value of C comments given by the solution to our differential equation. As you can see, these two curves human readable to be identical, and we saw in Figure 4 that if we subtracted these two, what each line is doing, difference, which is basically the error between the exact solution and our approximate solution, was very close to 0 down here, and there is just a slight modification here. If we look at this line 18, plot time versus amount of salt in the tank X, comma, and then in single quotes, line width, comma, 2. This makes the width of the plotted line a little bit thicker so that it's easier to see. Let's run this program. Save and run. And our graphs came quickly. Let's just move them over so that we can look at them. Okay, here's Figure 1, which is X versus T. Figure 2, the numerical approximation of the concentration versus T. Figure 3 is T versus the exact value of C, and I do have a slight typo right here. That should have been a T. And the fourth one up here, down here, error in the approximation, which is C minus C exact, and we can see that it's basically a horizontal line, looks like horizontal line, with the value constantly being 0. So as far as this graph goes, the error in our approximation was extremely close to the solution. The error is approximately 0 because our approximate solution and our exact solution were very close to each other in value. Here are the 4 graphs that we just saw. The numerical approximation of X versus T, the T-axis time is horizontal, X-axis here is vertical, and it's this curve. The amount of salt in the tank is increasing with time. For our simulation, the numerical approximation of the concentration of salt in the tank versus time is given by this plot. If we look at the solution to the initial value problem, if we find an analytic solution to the differential equation with the initial condition, we get the solution curve looks like this, and I don't see much difference between this curve and this curve. To see how much difference there is, let's subtract the C values from this and this and graph the error. The error in the approximation is this line, which looks pretty horizontal with a value very close to 0. So the results from our simulation were very close to the results of our solution to the differential equation. So what did we do? We considered a physical problem with dynamic mixing of fluids, salt water in this case. We set up an initial value problem corresponding to the physical problem. It was a first order linear differential equation. We analytically solved that problem and considered what it told us about the long-term behavior of the solution. And we also set up and ran a computer simulation of the physical problem using the programming language built into MatLab, and we saw that it did a very good job of approximating the exact solution in this case. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.